Now we will discuss what is gravitational field. See, every body having mass m creates a field around itself. It creates a field around itself such that if you bring any other mass in the vicinity, every body having say mass m will generate a field around itself such that if you bring any body of say mass m dash in the vicinity, in the neighborhood of m, then this body is going to experience a force. Get your point? This body of mass m will generate, every body of mass m is going to generate a field around itself, field in the neighborhood, such that if you bring any other body of say mass m dash in the vicinity, this is going to experience a force, right? Such a field is called gravitational field. This field is going to be called gravitational field, and gravitational field produced by any body of mass m depends on the gravitational field. Every body having inertia, it has got a region, it creates a field in the region around itself, and that is called gravitational field, which depends on mass of body and has got inversely proportional to r square. See, field means what? You understand what is field? Field is sphere of influence, a region of influence. It's a kind of region of influence, right? So every body of mass m creates a region of influence around itself such that if you bring any other body in the vicinity, then that is going to experience a force, right? Such a field, we call such a field as gravitational field, right? Gravitational field. And gravitational field is denoted by the vector g. So g, the magnitude of g, depends on mass of the body of which we are talking about the field. Gravitational field produced by any body of mass m, let me write it like this. Gravitational field produced by a body of mass m, or let's say the magnitude of g is say g, and that is proportional to mass of the body and inversely proportional to distance, square of distance. So g is gravitational field to any body depends on m upon r square, and to remove this constant we write it as g m upon r square, right? That's the gravitational field to any body at any point in the region. Getting a point? See, this dependence is quite obvious. See, if you talk about field of any person, we also have got a field. Every person has got a field. A person who is a good speaker has got a field. A person who is a good teacher has got a field, and a person who plays good guitar also has got a field. So on what factors do you think the field of a person depends? Field of any person depends on, or field of any object, or field of any person would be depending on some inner characteristic. Like one who is a good teacher, he has a good knowledge, a good way of teaching. So that is the inner characteristic on which his field depends. And field has got inverse variation with distance. That's quite obvious. That's for every object, whether it is living or non-living object. So that inner characteristic we are talking over here in case of non-living object is mass, and here it is proportional to distance square. So gravitational field is proportional to mass of the body of which we are calculating field on r square, and then we apply gravitational constant, right? We can also define it using the definition of gravitational force that we have used in previous videos. We can have a quantitative definition. People define it like this: the gravitational field, you know gravitational force, so using that we will define gravitational field of an object. Gravitational field of any body of mass m, gravitational field at any point P due to a body of mass m, or let me do it like this. Gravitational field, let me try to define it in general. Gravitational field at a point P in space, at a point P in space, due to any particle or system of particles is equal to gravitational field at point P due to any particle or system of particle is equal to the net, or is equal to the force experienced by a test unit mass placed at point P. See what it is telling you, what definition says. See, it says that if you have a single particle or a system of particle, you may have a single particle or a system of particle. See, in case of in mechanics, we have whenever we say system of particles, we have two kind of systems: system of discrete masses. System of discrete masses means I can have a point objects, say a body of mass m1, m2, m3, mi, mn, or the second kind of body we have is system of particle. We have a system of continuous distribution of masses. For example, body in the form of disk of mass m, or you can have a rod of mass m. That is continuous distribution of mass. Any arbitrary set material having some density rho. Rho can be constant also, rho can be space varying also, right? So in both the cases, this definition is going to hold good. If you want to find the gravitational field due to this system of particles, say at any point P, if you want to find gravitational field due to this system of particle at any point P, or gravitational field due to this system of particle at any point P, the definition says that the gravitational field at point P is going to be the force experienced by the gravitational force. The force we are talking is gravitational force experienced by 1 kg of mass. If I place here, wherever you want to find field, you place 1 kg body over here, 1 kg point object, 1 kg point object, test unit particle of mass 1 kg, whatever force experienced by the object of mass 1 kg, that is going to be the field due to this system of particle at point P. Wherever you want to find a field, you just try to calculate what is the force experienced by 1 kg mass placed at that point P. What is the force experienced by 1 kg mass placed at that point P? That's how gravitational field is defined. If you want to find gravitational field of this system of continuous distribution of mass of point P, same definition will hold good. You place here 1 kg and try to calculate the force experienced by this 1 kg. And try to calculate force experienced by this 1 kg mass. That would be gravitational field due to this system of particle over here. So if you are given any system of particles, system of masses, and you want to find field at point P, you just place 1 kg mass over there and try to calculate the force experienced by that 1 kg mass and that is going to give you gravitational field due to that system of particle. For example, I'll take a simplest case. Suppose we have a point object of mass m and I want to find field at point P, and suppose point P is at a distance of r. We want to find field at point P. We want to find field at this point P. Alright. Now, as per definition, the field at point P is going to be force experienced by 1 kg mass placed at point P. So, what is force experienced by this 1 kg mass? Force experienced by 1 kg mass is going to be G m into 1 by r square. That's the magnitude of force. And what is direction of force? See, gravitational force is always attractive. So, this body is going to pull this 1 kg towards itself. Getting a point? So, if I take it as origin, then what is the unit vector in this direction? See, the unit vector in this direction is ER. What is ER? ER is a unit vector in direction of increasing r, but your force lies in this direction. Force lies in this direction. So a unit vector in this direction is going to be minus here, and that's your gravitational field at point P. Gravitational field at any point P which is lying at a distance of r from the body of mass m is going to be this, where ER is unit vector in direction increasing r. So this will be, in nutshell, this is Gm by r square ER. The minus sign stands for attraction. Minus sign stands for attraction. Okay. So this is the gravitational field due to a single point object. Now, if you have, say, instead of single object, if we have, say, system of particles, say m1, m2, m3, m4, mi, mn, and we want to calculate field at point P, then what would be the field at point P? In that case, what you have to do is, we'll make use of principle of superposition. We'll calculate the field due to each particle at point P, and we'll take the vector sum. Just calculate, whenever you have system of discrete particle, you just calculate field due to each particle. This is a mi, ith particle, and suppose point P is, say, r vector. Then the vector from mi till point P is how much? This is going to be r minus ri. So the gravitational field due to ith particle is going to be what? G mi and square of this distance, that is r minus, where r is the position vector of point P where you want to find field, and ri is the position vector of ith mass square, and the field will lie in this direction. Field will lie in this direction, which is opposite to this direction. So what is the unit vector in this direction? This vector will be along r minus ri. So er along r minus ri, let's call eri, that will be r minus ri by magnitude of r minus ri. That's how you get the unit vector in direction of any vector. But your field is in this direction. It's only attractive. So field to any mass mi at point P will be towards the mass. So it is minus of this vector upon, let's put minus sign over here, r vector minus ri vector. This, all this is simply gmi r minus ri cube r minus ri. So that's the field due to ith mass. And if we want to get the net field, the net field is going to be G is sigma of Gi, and this is Gmi okay. So that's the field due to system of particle at any point P. That's the field due to system of particle at any point P. Okay, so this is the field, and I can proceed now because I don't have R1, R2, R3 numeric value of R1, R2, R3, but that's how you have to go. And while taking the sum, it's a vector quantity, so you have to take care of directions also. That's the formula. Okay, now if suppose this is for system of discrete particle, if suppose we are given system of continuous distribution of particle, suppose we are given this is a continuous distribution of particle, and we want to calculate the field to this continuous distribution of particle at point P. In that case, first of all, you have to choose a coordinate system. See, coordinate system is needed in order to locate this point P or locate the masses. So let's take a coordinate system. Then see, we have got the formula for gravitational field due to a point object, but this is not a point object, it's a continuous distribution of mass. It is a continuous distribution of mass. So what I can do is, I can see this continuous distribution of mass to be consisting of mass element, the infinitesimal mass, we call it dm, and this infinitesimal mass is considered to be a point object. So the formula that we have got for a point object, that can be used in calculating the field dm at point P. And this element, suppose it is lying at say r dash, and suppose the point P is r. In that case, the field due to dm at point P is going to be, the field due to dm at point P is going to be simply G dm upon, what is this distance? What is this vector first? The vector starts from Ri, r dash, and ends at the tip of r vector. So this is r minus final position vector minus initial position vector r dash. So distance square, the square of this distance would be r minus r dash vector square. Alright, and the direction of this field will lie in this direction. So what's the unit vector in this direction? See, this r minus r dash vector lie in this direction, but your direction of field will be opposite to this vector. So first of all, we will get unit vector in the direction of this vector, and then put minus sign. So unit vector in this direction is going to be r minus r dash upon magnitude of r minus r dash, right? And the direction of field is towards dm, so it will be in this direction. So unit vector in this direction will be minus of this. So minus of r minus r dash upon this. So this will give you minus G dm. Here you have r minus r dash and r minus r dash cube. This is dg. This is dg vector. Okay. And you want to find the gravitational field at point P to whole mass distribution, then you have to integrate it, but you have to integrate it taking care of the sign of vectors. You must take care of directions. The best way to do is, or the flat way of doing it is, you just try to break this dg into dgx I cap dgy j cap, you break it into component dg zk cap, and now integrating this, just integrate these components, and when you integrate the components are scalars, so you don't take care of direction, you don't have to take care of directions. But this may be at times very lengthy also, right? At times doing this is very lengthy, but this is a straightforward method, mathematical method of getting this G, that will give you G. But then that won't be needed. In fact, instead of doing this, you will always figure out a good way of getting integrating. You'll always find that while doing question, you'll find that some horizontal component or vertical component will cancel out, and only net vertical or net horizontal component will be non-zero, right? So that will be that we will be able to discuss only when we take up a question, right, where it is needed and where it is not needed. Okay, so that's the theory, that's the method of getting gravitational field to a system of particles. And what you are doing actually is, when you are doing summation or doing integration, you are doing nothing but you are applying principle of superposition basically. That is indirectly applying a principle of superposition. You are calculating the field to dm, and then you are integrating nothing but operation of summation, right? It's an operation of summation kind of thing. Okay, in next video we will do some questions. We will take the different cases and we will find the field with those mass distribution. Okay, so I'll stop over here. Thank you.